as you've been noticing here in your homework, this area function, the area function is what? Area function is what? The antiderivative of the little f, the thing that we're doing the area under. Okay, that is that key component, and once we know that all that chart kind of stuff, all those derivative relationships are in play. And we know that in that area function, that left edge, here we see the 0 and the 5, the left edge only determines what? On the antiderivative. The plus c, right? Because every time we do an antiderivative, like the antiderivative of x is 1/2 x squared plus c. So, and that graphically, that's just a vertical shift. So if we were going to graph the antiderivative, they would just differ by a vertical shift. Now we'll talk about that. So there's all those kinds of questions we can ask about the area function and doing areas involved. So that's the fundamental theorem part 1, right? Fundamental theorem part 1 is this right here, which basically says that the area function is the antiderivative. That's what that says. Remember, the integral, the area function in here is the antiderivative. You do the derivative of the antiderivative, they cancel each other out, you get little f, right? Now, that is the big idea of what's going on, and that is helpful in most of the problems that will be on the quiz tomorrow. Now, what's left to do, since a few of you have to leave, what's left to do is answer this question here. I mean, that's what we have left to do, is how in the world do I find that area, right? Because there's, if we think about what we have done. Matter of fact, since you guys are leaving, let's kind of change our order here a little bit. Let's go ahead and do this now, and then we'll come back and we'll talk about the homework and those kind of things. Okay? And you guys that have to leave, you'll have that option, and it's kind of 6 and 1/2 does the other. I'm going to take the quiz tomorrow, or wait until Monday. But see what you think, and you can let me know in the morning. But that is the question that is left. How in the world do we find this area? It's a curve, this parabola. How in the world do we do it? Well, we feel like the derivative, somehow the antiderivative must be involved. Somehow the antiderivative must be involved in helping us to find this area. Okay? And as it turns out, it is. And that is what part 2 of the fundamental theorem is. Okay? And so how in the world could we do this? Now, this part, I don't really care if you write this next part down, because it's not anything you're ever going to have to do again. Okay? We're going to develop the way that we are going to be able to work this problem right now. You're not going to have to do this on the quiz. You're never going to have to do this. Okay? So if you don't want to write it down, that's fine. But let's pretend, okay, so this is what I'm trying to do, is this integral right here. So let's pretend that I had big F was that area from -1 to x, and big G was that area from 2 to x, right? Same function, notice it's x squared up there. Of course, we call it t squared because we can't use x since we're using x in our definition of our area function, right? So we call it t squared, but it's the same thing, okay? Now, using some rules, and this is why everything we've done up till now, the whole fundamental theorem part 1 and this whole antiderivative stuff, the whole reason we've been doing all that is to get us to this point so that we can do this. Because this is what we really want to be able to do, right? In the 1600s, they needed to be able to find the area of oddly shaped regions. That's what we're talking about here. So all of this stuff has been developed and came about to get to this question, right? That's why we've done all this other stuff, okay? So just like how do you find the slope on a curve? Well, that's where the derivative came in. We do the derivative, we plug in the number where the point is, and boom, that gives us the slope of the curve, right? All that development about f of x plus h minus f of x all over h, all that stuff, slope formula, limit as h goes to 0, that all got us to the point where we could come up with those derivative rules and find the slope of a curve. That was why we wanted to do it. So, let's go back and let's use those things we've learned now to do this, okay? So one of the things we learned is that I could take this integral right here and I could split it into the integral from -3 to -1 plus the integral from -1 to 4. Couldn't I? Isn't that right? Didn't we learn that? It doesn't even matter that the -1 happens to be in between the -3 and the 4, but remember we said that didn't even matter, right? That's one of the things we learned, correct? Now you might be wondering why I did that, okay? And I don't blame you. And another thing we learned is, what if I flipped around the -1 and the -3 here? What if I flipped that into this? Then all of a sudden it would be opposite, right? So I need to do that. Does that make sense? So this area plus this area would be the same as this area, right? But if I flip this around, then that's opposite, right? So I got to put a negative on it, okay? And so then if I flip those around, since this one's negative and this one's positive, if I wrote the other one, if I wrote this one first, -1 to 4 x squared dx minus -1 to -3 x squared dx, right? Would you be okay with that? And what would be another name for the integral of -1 to 4? Hint, 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 look up here. What would be another name for this integral? Using an F, a big F. Isn't this big F of 4? Isn't it? Isn't that big F of 4? Because big F is defined to be the integral from -1 to x. That's big F of x. So -1 to 4 would be like putting a 4 there, which is like putting a 4 here. Would you agree with that? Right? Just another way of writing it. And then what about this other one over here? Isn't that just big F of -3? Right? Interesting. And isn't big F, what is big F again? What is big F? Isn't it the antiderivative of t squared or x squared? What's the antiderivative of x squared? What's the antiderivative of x squared? 1/3 x cubed plus some c that we don't know. Could we find? Sure, because we know that big F of -1 is 0. Remember we did that yesterday? Big F of -1 is 0. Now again, you're not going to have to go through all this. Now this part you might have to go through in a separate kind of problem. I might give you this and say, hey, find the formula for big F, right? Well, you need to be able to do that, right? You'd go that'd be 1/3 x cubed plus c, but I know that big F of -1 is 0, right? Remember that initial condition thing we talked about yesterday, right? We know that big F of -1 is 0, so therefore I could put a -1 in there. That'd be -1/3 plus c equals 0, so c is 1/3. So don't I know that big F is 1/3 x cubed plus 1/3? Isn't that what big F is? Now, what this is saying is that I need to do big F of 4 minus big F of -3. Are you with me? Big F, so what would big F of 4 be? Well, it'd be 4 cubed, which would be 64, times a third, so that'd be 64 thirds plus 1/3, right? That'd be what, 65 thirds? Wouldn't that be big F of 4? And what's big F of -3? Well, that'd be 1/3 x cubed plus a third. So now let's put a -3 in there. -3 cubed is -27. -27 thirds. -9 plus a third. What's that? -8 and 2/3, which would be -26 thirds. And then wouldn't I take this minus that? So it'd be 65 plus 26. That's 91 thirds. Isn't that this area then? Now again, you're not going to have to do this. I'm going to show you a shorter way. We're going to have a shorter way, but isn't that what that is saying? Yeah. Okay, now But wait a minute, where in the world did that big F come from with its -1? What if it would have been big G? That's just a, what's big G? What's big G? Keep asking the same question over and over, it's the same answer. It's the antiderivative of little f, just a different antiderivative, right? But what's different about it? Just the c, right? It's still going to be 1/3 x cubed. Let's change to red here. It's still going to be 1/3 x cubed plus some c, but this time the g of 2 is 0, right? Different initial condition, right? Now, I'm gonna really mess you up here. Not mess you up, but I'm gonna because I'm out of room, I'm gonna write over the top of this. What if I would have said, so now let's talk about the g function. So now we're getting 91/3, and we think, hey, maybe that is the area. Okay, maybe that is the area, but geez, how in the world did you come up with that big F? Where did that come from? Remember, this was the problem. We were just trying to find this. That's all we're trying to do, right? We're trying to find this. How in the world would I have known to put a -1 area function in there, right? Well, you don't. It turns out you don't have to. That's the beauty of it. Okay, I just made these up. Right? Different antiderivative. But look what we came up with. We came up with, hey, this area from -3 to 4 would be this, and I just rearranged it. And I said, oh, it's just that. Big F of 4, big F of -3. Well, I can do that. Big F of 4, I can find a formula for big F of 4, right? Because I know that's the antiderivative. So I just did the antiderivative, used my initial condition, that thing we were doing yesterday. Okay? Now watch what this would look like with G. G has a 2 in it. So I got to change this. I need that to be a 2, and I need that to be a 2, right? Now wouldn't this be true? The area from -3 to 2 plus the area from 2 to 4? Wouldn't that also be this area? Yeah. And then what if I flip these around? So what if I made that a 2? Wouldn't that be opposite if I flip those? Right? And then what if I rearrange this? So I brought this one in front, and then I made this one, oh, whoops, and then this one's a 2, right? This is a 2 here. And then so what if I change that and that to a 2, right? Isn't that all the same right here? Right? And what's another name for the integral from 2 to 4? Hint, hint, hint. The area from 2 to 4 is big G of 4. And what's the integral from 2 to -3? Oh, it's the same thing. It's a different antiderivative with a 4, and look at the 4 and the -3, they're right here. How can that give me the same answer? Because big G is a different function. But it's only different by what? The C. So if I take a different antiderivative with a different plus C, but then what did I do with that plus C? That was the 1/3 here, right? I put a 1/3 on this one, I put a 1/3 on this one, and then what I do with those answers? What do I do with these answers? I subtracted them. Well, what happens if this one has a plus C and this one has the same plus C and you subtract? Won't the C cancel out? The 1/3 just canceled out. Really, it was just the 64/3 take away the -9 is really what it was. That'd be -27. If you have 64 and 27 and add that together, that's 91. In other words, the C didn't matter. Holy mackerel. The C didn't matter. Then why do we care? Exactly, we don't care about it. So that's great because, so what we're saying, listen, so really what we're saying is if I want to find this area, take any old antiderivative. Take any old antiderivative and use it. It doesn't matter. Big F, big G, big H, big whatever. Left endpoint doesn't matter. In this scenario, because we're subtracting them, the C will just subtract away. So, voila, oh my gosh, this is almost as exciting as Fundamental Theorem Part 1. So why have we done all this stuff? To find that piece of area. It turns out that all you need is any old antiderivative of x squared. Well, what's the easiest antiderivative of x squared? 1/3 x cubed, the one that has 0 is at C. Take any old antiderivative of what's in here, and here's the notation we use. You might want to jot this down, then this part you might want to jot down. I call it right bracket notation. No, I didn't make that up. Wow, it's got a right bracket. That was really, really ingenious of me to make that up. The integral sign is not there anymore. The dx is not there anymore because think about it. We're doing, it's like if I say, it's kind of like if I told you this. If I said, if I told you to do this problem right here, what would you write for your answer? 2x. You wouldn't say, well, what happened to the dx? Well, that was part of what it was telling me to do. It was telling me do the derivative with respect to x, so I did it. Well, same thing here. The dx just goes away. We're saying do the integral with respect to x. Okay, we just did 1/3 x cubed. We did the antiderivative, right? So the dx just went away. The integral sign's gone away because we're doing what it said, which it says, let's do the antiderivative. Any old antiderivative will do. And then plug in a 4. Remember what we did over here? We plugged in a 4, then plugged in a -3, and we subtracted them, right? So just all we got to do is plug in a 4, so that would be 1/3 times 4 cubed minus 1/3 times -3 cubed. And if you think about it, that's exactly what we just did. We took the top number and the bottom number because that's what it ended up being here. The top number came first, the 4, the bottom number, -3, came there. And so 4 cubed is 64, so that's 64 cubed minus, and then this would be -27 times 1/3, so that's -27 thirds, ends up being plus, ends up being 91 thirds, and just like that, if we can do the antiderivative of this function, and that's why we're going to do a gateway test on antiderivatives, right? Because the only way this works is if we could do the antiderivative of what's in here. But if we can do the antiderivative of what's in here, all we have to do is plug in this number and plug in this number and subtract them, and we'll get the area. Not for me, that's for Isaac Newton, right? We're clap for Isaac Newton and Leibniz. Okay? That'll get it for us. That'll get us our area. Okay? Now, so the plus c doesn't matter, right? The left endpoint, it's good. It doesn't. We can take any old antiderivative and do it. So that is fundamental theorem part 2. Now, okay, fundamental theorem part 2 is this right here. Okay, fundamental theorem part 2. So while you're writing that, so fundamental theorem part 1. It's funny. Some books, when I was in school, these were switched around. Which one was called part 1 and part 2? And still, in some books, they'll be switched around. Okay? But we're going to use this. Why would the first one we did be part 1? Well, I think the people that call that one part 1, they think it's the most important because without that idea, without that concept, that the area function is the antiderivative, you couldn't get to this part. Okay? The people that call this part 1 are saying, but this one is useful. This is what we wanted. This is the one we use all the time. Okay? So this is more important because it's more useful. So the first one is important because of what it says, because that concept is so important. This one is important because it's useful. We actually can solve problems with it. Okay? And so what it's saying is if you want to do the area from A to B of any old function, little f, all you need is the antiderivative. Just pick any old antiderivative. We usually pick the one without the plus c on it, where c is 0. And put a b in, put an a in, subtract them, and you get the area. Okay? Yeah. Yeah, I don't know exactly. Well, I do too. Here, let me just write it down here, and you guys can take this with you. This is going to be pretty cool. You might want to check the website in case I might change my mind and give these guys more. Here, you guys can share it. Okay. I think that's it. All that really is, you guys, is practice using this. That's pretty much all it is definite integrals and using this. But the rest of it will be reviewing for the quiz and all that other stuff. Okay? All right. So, well, that worked out okay. Now, so that is the kind of, what do I want to say, the new thing here. So actually, why don't we, let's see, what might be best. Let's do this. I think what I'll do is give you some work time here in the middle, okay? So let's go ahead and do this for, oh, I don't know, maybe 20 minutes, let's say. And then we will come back together and talk about today's homework and kind of review, okay, this is what you have to do for the quiz, you know, kind of stuff, and so forth. All right, so let's do that. So here is going to be, at least as far as I can tell right now, let's finish the 5.3. I think what I gave you, if you look at this sheet, we did 1 through 8, we did 35 through 38, we did 43 and 48. So on that line that says 5.3, do the ones we haven't done. So that'd be 19 through 30. That'd be 49, 55 through 58. Okay? And then below that, it says LH, page 298. Three through 36 multiples of 3. So that's like 12 problems, 3, 6, 9. And that, again, is more just antiderivatives. Right? And so as you have questions, we can talk about them here. But let's take till about 10 till and work on some of those. And just using this fundamental theorem part 2. Okay? Get together and work on that a little bit, and we'll write a couple of them up here on the board. So just to give you something else to kind of look at, on 19 through 30, if that's where you're starting with the book ones, right? That'd be the first ones in the book, right? 19 through 30. I'm going to put a couple of them up here just so you have a couple more to look at. Okay, help me out here. On 20, we're supposed to do this integral. Now let's not forget what it is we're doing. We're doing this area. Here's square root of x, 0 to 4. You don't have to draw it. I don't think it said draw a sketch of it, but we're finding that area right there. Right? That's what this is doing. So square root of x is x to the 1/2. So we need the antiderivative of x to the 1/2. How do we do that? We're in this quiz tomorrow. You're going to have to do some basic antiderivatives, right? Now it's not a big emphasis on this quiz. Like I said, there's maybe a couple, 2 or 3, out of 10 or 12 or whatever problems where you have to do this. Well, how do you do the antiderivative of x to the 1/2? What's the rule? What do we do with the power? We add 1, so that would be x to the 3/2, and then, no, what do you divide by that. Remember, what's the antiderivative of x? We raise it up to a 2, and we divide by 2, right? It's 1/2 x squared, right? So how do you divide by 3/2? That'd be the same as multiplying by 2/3. Now think about that. You can check it quite easily. Do the derivative. Bring the 3/2 down in front. That would cancel the 2/3. Drop the power by 1. Sure enough, you get x to 1/2. So we got to be able to do that, right? The antiderivative rule was x to the n plus 1 over n plus 1. That's how you do antiderivative of power. So anyway, we would have that, and then we would put our right bracket 0 to 4, just like that, like we did on this earlier problem. That's what it would look like. The dx goes away, the integral sign goes away, because we did what it was telling us to do, which was do the antiderivative and plug these numbers in. So now we put that in, so 2/3, 4 to the 3/2, minus 2/3, 0 to the 3/2. This would be 16/3 minus 0, right? And talk in your groups about how you do 4 to the 3/2. Make sure you do that. Okay, I'll write up number 25 here. This is what your work should look like. No calculator, right? These are going to be no calculator problems. Remember on the sine curve earlier where they told us the area under the hump was 2? Well, at 25, you can see we're doing half the hump, and it comes out 1. But now we know how to do it. Before we didn't know how to do that. Okay, let's go ahead and go back to our seats, and maybe I can answer a few questions if you got any. If not, we'll go on and just kind of review some things, and then hopefully finish to the point where you can get back and work some more. Okay, was there any you ran into there that caused you issues or anything? Number 15 in the packet. Okay. Number 15, tell me what that one is. All over the square root of u, du. And you notice again, once we're back, and it was from 1 to 4. Now, you notice we're back in, when we're doing these definite integrals, it doesn't matter what letter's in there. Because remember, this is just a number answer when we're doing definite integrals. So if we step back and we think about what we've been doing, we started this integral section by chapter 5 by saying we want to be able to find the area under any. You guys all right? You look very comfortable. We started this whole thing by wanting to find the area under any type of function, including curved surfaces. And, and that's what we've come up with. That's where we've ended up. We now can take this. This is who knows what this graph would look like of this function right here. And we want to find that area underneath it between 1 and 4. Now, here's going to be the thing we're really going to emphasize next week. Next week, we'll really be starting to get ready for the antiderivative gateway test. We're really going to work on antiderivatives. So up until now, for tomorrow's quiz, we're going to stick with very basic antiderivatives. I would say this is beyond what you have to do for tomorrow. But here's how you would do this one. You would split it apart. First of all, we think of the square root of u as u to the 1/2. So I would take this, and now I'm going to keep the integral sign on it because I haven't done anything to it yet other than just rewrite it. So I would write this as u over u to the 1/2 minus 2 over u to the 1/2. Remember when we talked about splitting apart? Now, you could bring that u to the 1/2 up top as a negative 1/2 if you want and distribute. I just think, and I think I told you earlier this year, it's just easier to see if you split it apart. That's how I usually think of it. But either way works fine. Now, the next thing we want to do, and notice I'm still putting the integral sign on it, because all I'm doing is algebra here. Now I'm going to subtract those powers. So this would simplify to u to the 1/2, and then this one is going to be 2u to the negative 1/2. Now I want to bring that u up there. So I rewrite everything because I haven't done anything but algebra at this point. One of the things you will find out in doing antiderivatives that's different than when we did derivatives. When we did derivatives, everything had a rule. If it was a product, you did a product rule. Quotient, did a quotient rule. We had rules for everything. Antiderivatives are different. There's not very many formulas you have to remember for antiderivatives. The problem is you have to get them into a form so that you can do the antiderivative. That's the key thing with antiderivatives. So that's the work I did. Now I can do my antiderivative. It's just like the one we did earlier. Raise this up 1 would be 3/2. Divide by 3/2, that'd be 2/3 u to the 3/2. And then this one, what happens when you raise that power up 1? What's the new power? 1/2. And then you divide by the new power. So you divide by 1/2. Well, what happens when you divide by 1/2? That's multiplying by 2. And the 2 is already there, so that's going to be a 4 u to the 1/2. So you raise that power up 1, which makes it 1/2. You divide by a 1/2, which times it by 2, and you got that. Then I do my right bracket and the 1 and the 4. Now I notice I don't have the integral on there anymore. I don't have the du on there anymore. They went away because they were just telling me, hey, now you're going to do the antiderivative with respect to u. So we did that, and now I'm going to do a 1 and a 4. So I put my 4 in there. Now remember, this is all going to be no calculator, as I see some of you reaching to your calculators. And that's on your homework. I don't care. Now here's another thing you got to be careful of is parentheses. You've got to be careful here. When I put my 4 in, I got to put 4 in both places, so that's that. And now I've got to put the 1 in. So I get 2/3, 1 to the 3/2, and I get 4 times 1 to the 1/2. So, you know, the gateway test will have more of this. The quiz on tomorrow will have a little bit of this, maybe 2 of these problems. And one of them might get kind of ugly like this with fractions and stuff. You won't have to do this splitting apart and all that. But I might give you this problem right here, right? On the quiz tomorrow, I might give you this, the one that's in the box, right? And have you do that antiderivative and go from there. All right, now we need to finish this. Now 4, you do the square root of 4, which is 2, and then you cube it, that's 8. So that's 16/3. 4 to the 1/2 is 2. 2 times 4 is 8. Okay, over here, 1, that's just 1. Times 2/3, and that's just 1. Okay, so we got this. Okay, so now we need to get some common denominators. That'd be 24/3. So 16 minus 24/3, that'd be negative 8/3. 2/3 minus what? 12/3. 2/3 minus 12/3, that'd be negative 10/3. So we'd end up with negative 8/3 plus 10/3. The whole thing ends up being 2/3, right? So yeah, you might run into one tomorrow where you get into some fractions or something like that, but no more than that, okay? So it's a small part, couple of these types of things for tomorrow, okay? Fundamental theorem part 2, all right? Which is, again, the culmination of everything we've been doing, because that's really what this was about. I mean, that's what this whole, where we were going with this. Now, what we'll do later, and then we're going to practice, antiderivatives, practice doing these, and then later we'll get into applications. Where is this useful? Just like we do with derivatives. We found out with the chart, derivatives were good at finding maxes and mins and rates. And so we had all those applications in chapter 4 that involved rates and maxes and mins and so forth. Well, where is this area thing useful? We already have seen one, the velocity curve. If you do the area under velocity, it tells you how far you've traveled. That's one place where doing an area is useful. Okay? All right, so that is fundamental theorem part 2. So let's move on and talk about the homework for today. All right? The homework that you had. I would like to start back here. This was problems 12 through 14. Okay, the very beginning of your homework today. Now we're going back and we're focusing on the area function stuff, right? The area function is the antiderivative. Since it's the antiderivative, we can do all these different kind of questions like we've done before. Old stuff looked at in a new way. Okay, so here's the stuff we had on 12. We knew the little f graph was positive. What did question 12 say? It said show that big F, is that what it was? Big F was equal to G plus C? Or do I have that backwards? You got your book on that page? Somebody? Maybe I do. G of X, show that G of X, so this is very similar to a problem we did the other day. Show that G of X is equal to F plus C, and it asks if C is positive, I think. It says something about C being positive. Well, the F graph is the area, right? The F graph is the blue area from 0 to X. So the F graph is this area here. The G graph is this area. Right? Which of those is bigger? Isn't this the one? Is this the question? And we did not do this one yesterday, right? Right, in yesterday's homework, right. Okay, which one of those is bigger, the blue or the red? The blue is bigger. The blue is F. This one's bigger. Did it ask? Oh yeah, ask if C is positive. Or did we talk about 12? Or did we talk about, we did 8. Didn't we? Or maybe we did go on to 12.
I think you did do 12.
Maybe I did. Maybe I just said, hey, what about number 12? And even though it wasn't part of the homework. Okay. So big F is bigger. So for them to be equal, what's C got to be? Negative, right? So the question was C positive? No, it would have to be negative. You're right. I think we did talk about it. Okay, 13 and 14 then. I know we didn't talk about these. Explain why big F of 6 has to be greater than or equal to 6. Somebody want to tackle this one? Little f is above 1 here.
So that means that if it's 6, x is 6, then it's what's here.
So the area, so big F of 6, I would go back to this. What's big F of 6? Well, that's a 6 plugged right there, which means a 6 plugged right there. So big F of 6, so a good explanation would say the big F of 6 is the area from 0 to 6. Well, if it's above 1, what's the area from 0 to 6? Right here. Isn't that a rectangle? 6 by 1. And we know that the function's above that. So doesn't the area have to be more than 6? Absolutely. The area has to be more than 6 because of that. Now, does anybody recognize that question? It's the speed limit law. Now, speed limit law didn't have anything to do with area. But remember, we said this is new ways of looking at old stuff. Little f is what in this scenario? Little f's the derivative, right? Because big F is the antiderivative. Little f's the derivative. The derivative is the slope. the derivative graph is always above 1. So the slope is always above 1, right? The slope is always 1 or more. What do we know about big F? What's the initial condition that we get for free here? Don't we know that big F of 0 is 0? Remember those speed limit law problems? They would tell us that big F of 0 is 0. So you know the big F graph starts at 0, 0, right? Because that's the area from 0 to 0 here. Big F starts at 0. The slope is always 1. So if you go over 6, finish it for me. If you start big F at 0, 0, and you go over 6, you have to go up 6, because the slope is 1, rise over run. You go over 6, you got to go up 6, so the big F graph at 6 has to be 6 or more. Speed limit law. That's speed limit law. But now we see it in terms of area. We see it in terms of area, because since the big F graph is above 1, the area from 0 to 6 would be above this rectangle, which is an area of 6. Okay, what about 14? 14 is the same scenario. Now, you didn't have to notice that was speed limit law. If you did what Jared did and just said it in terms of area, that's great. That's fine. Okay? Is it possible that G of 10 is 3? Now, let's do that in terms of area first. G of 10 means what? G of 10 means what? The area from 5 to 10. Could the area from 5 to 10 be 3? If this was 10 right here, could this area from 5 to 10, could that be 3? No, it's got to be at least what? 5, because you got this piece right here that you know is in there. You know the graph's above 1, it's got to be at least 5. And again, the same argument, right? Since we know that, talk about slope, since little f is the slope, and it's above 1, if you go, and what's the initial condition we get for free on G? G of 5 is 0. So that means on the G graph at 5, you're at 0. So if you go over 5 more to 10, you got to go up 5. So you would have to be at 5. G of 5, G of 10 has to be at least 5, which we just saw with area. So no, there's no way it could be true. All right? New ways of looking at old stuff. All right. Now, you guys tell me from here what ones you want to look at. 5.2, 5.3, the rest of the homework. Which ones you want to talk about? 48 on that.
Yeah.
Okay. Okay. Yeah. Let's do that. So let's talk about 48. Now on 48, it said show that this. Let's see. Do I have a picture? I don't have that picture. Okay. Show that this is not equal to this. Now, don't worry so much about the t's and x's and what these have to be t's because they're inside the integral, right? This is dt because it's inside the integral. Here, this is outside, so it's x. But okay, those aren't really any part of it. Show this. What is this really saying? This is fundamental theorem part 1 right here. Okay. Now, fundamental theorem part 1. How do we read this? This is derivative of the antiderivative. Remember that? I mean, that's what we said. And according to fundamental theorem part 1, this side should be equal to what? Little f of x, right? Not t, but x, right? That's what fundamental theorem part 1 says. Here it is right here, right? I mean, that's it. I mean, that left side is word for word fundamental theorem part 1. But why is that? It's because it's the antiderivative. It's the derivative of the antiderivative. They undo each other. But now let's think about it here a minute. Let's actually piece that out just so we understand fundamental theorem part 1. This inside's the antiderivative. Let's call it big F. It could be big G, big H, whatever. But let's call it big F. It's got what on it? Any antiderivative. Plus C. Now that's determined by that A, right? Whatever that is. So this inside is like big F plus c. So this is kind of like saying the derivative of big F plus c. Now what happens when you do the derivative of big F plus c? What do you get? The c will go away. Now what's the derivative of big F? Little f, right? So it doesn't make sense if that's what we get, right? On that side. Now, what about this side? Well, let's start on the inside. What's the derivative? Oh, is this a t? Yeah, that's a t. What's the derivative of f of t, little f of t? That's f prime, right? And so let's do that. So let's write that as f prime of t dt. Now, what does this mean now? What does this mean? Antiderivative of f prime. What's the antiderivative of f prime? F, and what would be inside of it? X, right? Not t, because of that. Plus, you see the difference? So what they're really saying is they're saying, doesn't matter what order. You do the derivative of the antiderivative, here you do the antiderivative of the derivative. They both should cancel each other out, right? It's like square root and square, or square and square root, right? Which order do you do it? Are they the same? Well, it turns out they're not the same, right? Because when you do the antiderivative last, you have the plus c. When you do the antiderivative first, you have the plus c, and then when you do the derivative, the plus c goes away. That's why. Okay, that's why they're not the same when you do them, right? They both seem like they should undo each other. But what I like about that problem is just make you think of area function as the antiderivative, right? Area function is antiderivative. Whenever you have antiderivative, you have a plus c. Okay, what happens with it? Of course, we saw in fundamental theorem part 2, the plus c didn't matter, right? Because we're subtracting. We're doing the antiderivative minus the antiderivative. You know, with those numbers plugged in, the constant part doesn't matter. So we can pick any old antiderivative. All right, so that's good. What about, let's talk about 24 through 28. I actually want to talk about that too. Now that's back on section 5.2, I believe. Or maybe this. Yeah, that's back in 5.2. That other one was in 5.3. Let's talk about 24 through 28. Okay? Now, 24 through 28 was this picture. We don't really have a picture. But what we had is we had big F was this antiderivative, big G was this antiderivative, big H was this antiderivative. Now they're all the same except for the C, right? They're all the same except for the C, which just means their graphs would be all the same except shifted up and down. Now, here's what I want you to get out of 24 through 28. Where is big F increasing? Now, first of all, let me draw a graph of little f here just to help us out. Let me draw a graph of little f. And you remember I had this up here yesterday. It's a line. Little f is this line right here. So it came up and it went like this. And it crossed right here at negative 2/3. Right? That's where it crossed. All right? So where is big F increasing? Well, where was big F increasing? This is little f. When little f is positive. Isn't that just from the chart, right? Who cares about area? Who cares about area functions here? We wouldn't even need to worry about it, right? It's when it's positive. That'd be from negative 2/3 to infinity, right? Where is big F decreasing? From negative infinity to negative 2/3. Why? Because that's when little f is negative. Is F concave up anywhere? When is big F concave up? When little f is on the chart. Big F is (26). Big F is concave up when little f is increasing. So when is this one increasing? Everywhere. Is big F concave down? Never. Now, but here's the real question. So we need to be able to do that, right? I don't care about area here. We don't have to do area because it's this derivative-antiderivative relationship, so it's chart stuff. What if 24 was G. Where is G increasing? Lacey? It's the same thing. Because how is G different than F? Big F. Just shifted up or down. If you move a graph up or down, does it change where it's increasing or decreasing? Does it change where it's concave up or concave down? Wouldn't all these questions be the same? Because little f is the derivative of big F, it's the derivative of big G, and it's the derivative of big H, right? All three of these are the antiderivatives of little f. We said when f prime is positive, when f prime is negative, when f prime is not f prime, when f is increasing, little f, when little f's decreasing, negative, when little f is increasing, when little f decreasing. Little f doesn't change, right? Little f doesn't change in these parts. Big F, big H. Okay, so what I wanted, so I point that out, and I just got another example for you up here then, is, okay, let's pretend that this is little f right here. Here's big F. Let's say it was the integral from 0 to, I just made these up so I'm not sure they actually match, but whatever. This is little f. So it's a parabola. Well, it's an x squared. What's the antiderivative going to be? A cube. A cube, right? I mean, this is some squared type of graph. So the antiderivative is going to be a cube, right? And of course, we did this way back in chapter 1, right? Little f is the derivative, so it's positive, so this graph's going up until here. What do we got? Local max right here, right? Local max. Then we got negative, it's going down. Then we got local mid, right? Doesn't that match? Right? That's what it should. So that's little f, that's big F, but here's big G. So, but now what we've added to this, new way of looking at old stuff. So that's all old stuff. The new stuff is, we have a new way of talking about the antiderivative. It could be the area function, right? This one might start at 0 for its left edge. This might start at 2 for its left edge. What changes? Only difference is vertical shift, right? So now, if I ask you, where's the inflection point? Where's the inflection point here? On this one? And on this one? Both. Where's the local max on this one? -2. Where's the local max on this one? -2, right? The vertical shift doesn't change any of the chart stuff. Increasing, decreasing, local max, local min, none of that. Doesn't change any of it. So the left edge, it doesn't matter. Big F, big G, whatever. If this is little f, all those chart questions are the same. So sometimes people get caught up in trying to, oh, but this one starts here, and this one starts here, and whatever. Now, when does that matter? When do you have to care about the left edge? Well, remember on this one here, let's see, maybe I deleted it already. I might have deleted the work we did earlier. But when we were looking at this problem right here, and I said, if I said find a formula for big F, right? Well, that's like saying find the C, right? If you need to find what the C is, then yeah, the left edge matters, right? Because if you change the left edge, then you get a different C. So if you had to find it, remember what we did here? We said, well, the derivative would be 1/3 x cubed plus C. And then our free initial condition is big F of -1 is 0, right? And then we plug that into there, and we found the C, right? So that's when it would matter what the left edge. So I don't want to talk like the left edge doesn't matter. It matters. But if you're asking a chart question about the antiderivative, then it doesn't matter. Vertical shift doesn't change where it's concave up or concave down or increasing or decreasing. Those things, right, don't change if you do a vertical shift. But if they want what's the formula of big F or the formula of big G, and you've got to find what C is, then yeah, then you would use that fact, to do that. Okay? Or if they want you to find actual areas. Okay? So, and we'll talk about that here in a minute. So I've got kind of some review ideas right here that you might want to write down for a quiz. And then let's go through this, and then I'll let you go back and work. So, try to summarize here what we have learned, what we have done. Okay? So when we started out, section 5.1, we were finding areas geometrically. Okay, so if this was little f here, let's say, and I ask you to find, let's say I said that g of x was equal to the integral from 2 to x f of t dt, let's say I said that, right? And so now if I ask you to find g of 4, well, that's the area from 2 to 4. Now, we would find that using geometry. We would just, right, there's no formula for that, so we're not doing an antiderivative, right? We're just finding areas. Maybe some triangles, some trapezoids, maybe that's a half circle, right? That kind of thing. So that's where we started with it. So you're going to have to do some of that on the quiz. There'll be a picture, something like this, and you'll have to find some triangle areas. Now remember, you need to be able to figure out where this crosses. If it doesn't cross the x-axis at a really nice point, then you might have to use the slope of this to figure out where that crosses. Like we had that one yesterday, it was negative 2/3 is where that crossed. So you've got to be able to figure that, because that'll affect your areas. Okay? And then if I give you a different area function that has a different left edge, and that would change, right? I mean, so there the left edge would matter if you're actually finding some areas, right? Then that's certainly a part of it. All right, so that's how we started. And then we also had those formulas for splitting up our integrals. Now, you're probably not going to use that as much now. Remember, I don't know if you need to write this down, but the other day when we were, say, doing this integral right here, and it was x squared plus 3. Well, when we were doing section 1, we didn't know how to do x squared area, right? So what did we do? We split that into x squared dx plus 3 dx. And then this one we could do. 3 dx we could do by just doing a horizontal line, right? We could do that area. This one we didn't know how to do, but they told us in the directions how to do it, right? Well, now that we've learned how to do this with antiderivatives, right? Wouldn't we just do our fundamental theorem part 2 now in this? We just go 1/3 x cubed plus 3x, do our right bracket, right? And we would just do so we really don't need this part as much. Where we would need it, I suppose, is if we did some problems, I know, where they told us the integral of h from 2 to 5 is 12, and the integral of f from 2 to 5 is negative 3, right? And then they would ask you, what's the integral from 2 to 5 of 3h plus 4f, or something like that, right? And then you would maybe split that apart, pull the 3 out in front, that kind of thing, right? So you still might want to do that where you have to split them up, but not on these examples here. Now that we know how to do those antiderivatives, you would just do your antiderivative. But here, that doesn't help you with the h and the f, because if you don't know what those are, you can't do their antiderivative. Okay? So that's what you really got to remember, from that first section. Okay, the second section is where we did the area function is the antiderivative. So all this chart stuff, right? The left edge is the plus c of the antiderivative, which when you're doing the chart stuff doesn't really matter, like we were talking about, vertical. So we had a lot of those kind of questions. That speed limit law kind of thing was in there, stuff like that. Okay? So looking back at that homework we've done over multiple days, those kind of things. And then 5.3, really we emphasized today, was the fundamental theorem part 2, which was just now that's that big F of B minus big F of A thing, where we can now do an area of any kind of function now, as long as we can do its antiderivative. As long as we can do its antiderivative, we can do that. And that's really it. I mean, that's pretty much what's going on. So this last thing is mostly about just calculating and doing those antiderivatives. You have a little bit of that. This part, finding them geometrically, you're going to have a little bit of that. Some triangles, some trapezoids, having to do some areas there. You're going to have some of that. And then a lot of the questions are going to be the stuff we've spent the most time on. That was this stuff in here, that whole antiderivative stuff, and the chart, how it relates to the chart, and just new ways of looking at some of our old stuff. And just going back over those homework problems is a good way to look at that. Okay? All right, you can have the rest of the time to keep working on those, on the homework and reviewing and asking me if you've got some questions on any of the other homework there that we didn't get a chance to talk about. Love to help you out with that. I will be here in the morning, I promise.